chapter 2, basically, I think your book puts, in section 1.4 of your book, they introduce this idea, which is why that very first problem says reference section 1.4. But basically we're starting chapter 2. Okay, chapter 2 is about something called the derivative. And pretty much everything you really need to know about the derivative in terms of, if you know what's at the top of this paper, you should be able to come up with all the things that we use a derivative for and the little rules that we use. Okay, so this summarizes the main idea about the derivative. The derivative of a curve is the slope of the tangent line. So again, tangent in this case means it slices through one point. So it sort of just kind of rides the curve, but it technically only slices through one point in a little neighborhood. It's not really accurate to say it only goes through the curve at one point, because your curve could come back around and your tangent line could actually, cut through it at another spot, but not in the little neighborhood. So the phrase going off on a tangent kind of, I think, comes from the idea that you start off, intersecting, but then, your line goes off from your original curve. But in a little neighborhood, your tangent line is agreeing pretty much with your curve. And because of that idea, the derivative can also be considered as an instantaneous slope or an instantaneous rate of change. And if you have some application where x and y have units, then the units of your derivative are the units of y divided by the units of x. Okay, and those ideas put together kind of summarize what is important about the derivative. But we have an entire chapter all about the derivative. In fact, 2 chapters. Chapters 2 and 3 are all about the derivative, and so we're obviously going to do all kinds of stuff. But when it all comes down to it, this is the main idea. Okay, the derivative is telling you what is the slope right at this point. And why I was asking if people had the apps on their phones was because I have an activity in which we go out and walk around the campus, and as we're doing so, we try to make an elevation chart of our walk, and then from that determine things about the slopes that we were walking. So when we were actually walking uphill steeply, we should notice that in our elevation chart, and the value we get for the slope there should be higher than the values at other places. And there's places where you reach the top of a hill, then you start to go back down, and we can talk about what's going on with the slope at the top of the hill and so forth. So that was what I wanted to do. It does depend on if it's pouring rain. We don't want to be out doing that. It's getting to the point where it's starting to get darker earlier, and so we'd have to go out kind of right away. But anyway, that's what. So I'm telling you this so that if people think they can come up with that app, maybe we can try to do that activity on Thursdays. But in the meantime, we can work with the examples that are in your book. So I'm just suggesting that you might want to go through and read through section 1.4. And in the meantime, we're going to work through these examples. So question A says the displacement in meters of a particle moving in a straight line is given by that particular polynomial. What that means is you sort of have some starting point, and a particle might be moving forward, it might be moving backwards, but it's moving along a line, and you're tracking it's displacement from start, okay? So displacement means change in position from a starting point. And a positive displacement means you are moving in what would be considered a forward direction. A negative displacement means you're behind your start point. So you can have a negative displacement. If you're talking about distance, displacement is actually different than distance. Distance refers to just, it's positive, but it's total length covered. And it's always positive. Think about that, the difference between these two words in terms of somebody running around a track. If somebody goes to a track and runs around a track, they might run 5 miles, so that's the distance they ran, but they might stop at the same place they started, and what would be their displacement? 0. Okay, so that's the difference between displacement and distance. Distance is total length covered, and it's always positive, whereas displacement is in reference to some starting point. They might be the same thing, they might be the same number. If somebody ran 5 miles straight ahead, if their displacement and distance would be the same, but in general they're not the same. Okay, so our particle's moving in a straight line, so that means we're just going back and forth on a straight track. And t is in seconds. Part 1 says find the average velocity between 3 seconds and 4 seconds. Alright, so let's... we don't necessarily really need our graphing calculator for this, but it could speed up what we're doing. Let's see, t squared minus 8t plus 18. So x squared plus 8. Was it plus 8x? Minus 8?
Minus.
Or was it the minus from
Yeah,
the
minus.
8?
Yeah, minus 8t.
Okay, minus, okay. And then was it plus 18 or minus?
Yes, plus.
Okay, I had those mixed up. So then, okay, so I'm just going to go into the table. It plugged 3 in for me, and we get 3. You plug 4 in, you get 2. Okay, so Roman numeral I is asking us to find the average velocity. Okay, well, it's not really telling us what to do, but remember at the top of the paper, I put all the important things about the derivative, and the very last thing I mentioned were the units of the derivative are your units of y divided by your units of x. And so in this case, our units of y are meters. Did it say meters, or is it?
What is the displacement in meters?
In meters, okay. And x is in seconds. Okay, so meters per second, that's a velocity. That's what we kind of know of as velocity. So when they're asking for the average velocity, they're asking us to find the average rate of change in meters per second. And they gave us 2 specific points, so what we're going to do is we're going to take the y value at 3, well, I guess we'll go from 3 to 4. Y value at 4 minus the y value at 3. Okay, and I'm finding the average slope right now between those 2 points, which is going to be the average velocity of the particle when I interpret the units of the slope. So S of 4 was 2, S of 3 was 3. So I get negative 1 over 1, so negative 1. So negative 1 meters per second is my average velocity. And the fact that it's negative means that I am moving backwards. Usually backwards means back towards the start, but it's kind of all relative to what you defined in the first place. But in terms of our textbook, unless you're told otherwise, away from start is going to be forward, positive. Back towards the start is going to be negative.